So now we look at another example where we're basically using a corollary to the mean value theorem to prove an inequality. And the example we consider is the following. So this is this quotient here plus the arctan of x being less than this number here. So our goal in life is now to prove that this holds. And let's just, so we don't forget it, write the corollary of the mean value theorem that we're using here. And we're writing it a bit sloppily now, but it's if f prime is positive, this implies f increasing. And if f prime is negative, this implies f decreasing. So that's more or less what we're using. So I mean, a careful statement of this corollary is much longer, but this is the essence of it. Now, what do we do? So there's basically one way to do this now, and that's, well, there are some cosmetic choices we can make, but let's move everything here to one side and call that f of x. So here, this is just a constant, so it doesn't matter so much, but if this also depended on x, it would be crucial. So this is true if and only if I have the same expression here. So I just move this to the other side. And now I give the left-hand side here the name f of x. So I'm defining this to be f of x. And my goal in life is to prove that f of x lies below the x-axis. Now, first of all, when I make this definition here, let's figure out what its domain is. So here, the domain of f is, well, this constant doesn't make a difference. Arctangent has all of r as its domain. And here I'm not dividing by 0 for any x. And up here we're defined for all x. So the domain here is r. Because this is a combination of arctan x and a rational function here that's defined on all of r, then f is continuous on r, or we can just say that f is continuous. And similarly, f is differentiable. So it's continuous and differentiable on all of its domain. Now, what's the point? So the point now is to compute the derivative of f, make a table of signs for the derivative, get a crude sketch of f, and then try to read out this inequality from that sketch. So let's compute f prime x. So we need to use the quotient rule here. This means I'm first doing the derivative of him multiplying by him. So his derivative is 1. I'm getting this. Then minus this guy multiplied by this guy's derivative. This is 2x. So let's just put that immediately. Now this is all divided by this to the square. And then I have his derivative. So notice that these things are very similar. So this is an exercise that's cherry-picked to have nice computations. And the derivative of this guy is just 0. So in order to set us up to produce a table of signs for this guy, we need this on factorized form. So I put this on a common denominator. So this means I'm getting all of this minus, well, 2 square root of 3x minus 2x squared plus this guy. Well, to get this denominator to be the same as this, I need to multiply by this thing. So I get an extra factor like this. Then I have 1 plus x squared squared. And now I try to simplify a little bit. So this guy gets killed by those two guys. And what's left is the 1 here. So that gives me a 2. So I'm getting here 2 minus 2 square root of 3x like this. And this factor down here. And now to get this in a more readable form, I'll factor out 2 square root of 3. So I'm left with x minus 1 over square root of 3 like this. And then I have 1 plus x squared like this. Now this makes the table of signs rather easy because this is the only thing determining the sign. Well, this and the minus sign here. So if I make a real line here, the sign flips at 1 over square root of 3. 1 over square root of 3 like this. I have my factor, so let's just do minus x minus 1 over square root of 3. Nothing else here affects the sign, so I don't care. This is 0 here, and then negative here, and positive here. What does that tell me about f prime? Well, f prime has exactly this sign, so I don't have to do another line for him. So we can go immediately to f, and this is the point where I use this corollary. So now I deduce that f increases here and decreases here. So here we have equal max. And then we're going down here and here. So what was my question? My question is if this f here is always less than or equal to 0. And this is equivalent to asking if this thing here is at most 0, this value here. So we need to compute f at 1 over square root of 3. So let's go a bit down. So f at 1 over square root of 3. What's that? Well, we have this thing, which, well, let's hope to get nice numbers here. 1 plus a third. And then we have the arctangent of 1 over square root of 3. And then we have these guys here who will hopefully help us. So what's the arctangent of 1 over square root of 3? Well, if this is the exam, I'm crossing my fingers that this is one of the few values of the arctangent that we can compute exactly. So I'll do my table of sines and cosines here to try to deduce this. I'm good. So this gives me sine is 1. This is a half. And well, I'm really bad at remembering this. So I'll just do 1, 2, 3, 4 here. And here I do 4, 3, 2, 1, 0. And then I divide all the numbers here by 4. And then I do all of their square roots. Then I'm good. So then I can see, so let's clean this up into new rows. So 0 divided by 4 square root is 0. 1 divided by 4 square root is a half. And now finally for the tangent, we'll have, and now finally for the tangent, we'll have 0, 1 divided by square root of 3, 1 square root of 3, and well, infinity, you could say. And gee whiz, since the tangent of pi over 6 is 1 over square root of 3, the arctangent of 1 over square root of 3 will be pi over 6. So here we see that this is pi over 6. And to get this value here, I just needed to have memorized this sign 0, 1, 2, 3, 4, cosine 4, 3, 1, 0, and then divided by 4 and square root. So I think this is a nice little cheat, you could say. So where does this lead us? Well, let's see here. So we need to simplify this a little bit. Well, first of all, we can see that this cancels this. Okay, so yay. So now it's this versus this. So let's simplify here a little bit. So we have square root of 3 plus 1 over square root of 3 divided by 4/3. So that's 4. And I multiply this by 3. And then I remove square root of 3. Multiply this in, I get 3 square root of 3. These two together give me square root of 3, still divided by 4. And I have minus square root of 3 here. And what is it that I want to find out? So I just want to show that my f is always negative. So I just want to show that this point here is negative. So I need to figure out whether this is negative or not. So to do this, I can insert smaller than 0. And then we can see if we can get this to be equivalent to something we know to be true. So now I can, in fact, well, I can cancel square root of 3 everywhere. So this is true if and only if 3 plus 1 divided by 4 minus 1 is less than 0. And this is the same as if 1 minus 1 is less than 0, which is the same as if 0 is less than 0. Oops, contradiction. But let's take a look here. So in fact, I needed to get this less than or equal to 0. So I needed to get this less than or equal to 0. So this is what I needed, but this is of course true. So this is true. So this value here is less than or equal to 0, meaning that f of x is less than or equal to 0 for every x in the domain of f. And please notice that we've proven that this value of f is less than or equal to 0. And since this was the maximum value of f, the global maximum, this means that f of x is less than 0 for every x. What does that mean? Well, this expression here is less than or equal to 0 for every x. This was equivalent to this inequality holding, which was the thing we needed to prove. Hence, we have established this inequality.